Something that we have discussed briefly as we've gone through this is mass and weight and the force of gravity. And it is useful for us to discuss the difference between all those things. Your mass is a fundamental property of the matter that makes you up. The mass of any object in the universe is a fundamental property of the protons and neutrons and electrons that you use to construct that object. And so that does not change based on what planet you're on or what the local gravity is like. Your weight, on the other hand, is the force of gravity that is acting on you. Thus, on a planet with different gravity, your weight will change. This is very annoying for people who grew up with the imperial system with pounds and such, because we don't really do a good differentiation between mass and weight in our system, in pounds and such. It's a little bit easier to see in the SI unit system, in the metric system, because you can measure mass in kilograms and weight in newtons. Question, so if we took our weight divided by the Earth's force of gravity, then we'd have our mass. We'd probably have to convert to kilograms. Yes, almost. If we took our weight and divided it by Earth's acceleration due to gravity, then we would have our mass. The distinction is subtle, but the force of gravity is actually equal to your weight. The force of gravity just by itself is equal to your weight. They are synonyms. They are defined to be the same thing. So you can see with this equation here, the force of gravity, F sub g, is equal to the weight, by definition, in effect, and that changes on every planet, and that is equal to the mass of that object, which does not change, times the acceleration due to gravity, which is 9.8 meters per second squared on Earth, and 3.8 meters per second squared on Mars, and 1.6 meters per second squared on the moon, et cetera, et cetera. Obviously, we're going to be dealing mostly with the Earth in this class, although I will probably throw you a few random questions where we look at other planets, what's going on other planets, just for fun, just to see what's going on, just to give you another number to multiply by. I do want you to memorize the number 9.8 meters per second squared, as we've discussed before. It's just one of those really convenient numbers to just know. I'm not going to be too hard on you if you use 9.791 or whatever the value is. As I said before, it changes depending on where on Earth you are. You'll have a slightly different value for the acceleration due to gravity. And so I just say, let's all use 9.8. It's going to be close enough for everyone on Earth. So use 9.8. Remember that Canvas has a hard time if you plug in a number that is not close enough to the accepted value. So try to just use 9.8 on all these kinds of things. Let's talk about this example. This horrifying looking torture device is called an Atwood machine, named after its devious inventor. A string that you can see here in blue connects two masses going over a pulley, which you can see here. How fast do the masses accelerate? And we're going to do this with all variables. Everything we're going to do with this one is going to be variables, which I know many people don't like, and that's okay. We can assume that one of these masses might be more massive than the other. We're not told that. M1 down here and M2 over here, they might be the same mass. You know, M1 could equal M2. We're not told one way or the other. M2 could be heavier than M1. It could have a larger mass than M1. M1 could have a larger mass than M2. We don't know, but we can create an equation that will let us account for all of those different possibilities. The first thing that you always need to do on a problem like this is draw it. And we already have it drawn there. The second thing that you always need to do is make free body diagrams for your masses. For every thing that might be moving in your problem, you're going to need to create a separate free body diagram. So we have two objects that could be moving, and therefore, because we have two objects with mass that could be moving, we need to have two free body diagrams. I see some questions. They could have equal weights, but have different masses, right? Since they're different sizes. If they have the same mass, then they have to have the same weight if they're on the same planet, because weight is equal to the mass times the acceleration due to gravity. So two objects on the same planet are going to have the same acceleration due to gravity. So same mass, same weight, different mass, different weight. Other question, does T stand for the normal force? T, in this case, stands for the force of tension in the string. Let's look at each mass. Well, we don't really need to look at each mass because they're fundamentally the same. Mass 1, we'll look at that. What are the forces acting on mass 1? This is how you draw a free body diagram. You look at a mass that could be moving, and you say, okay, what are the forces acting on that mass? Well, on mass 1, we're going to say that this is all happening on Earth, because why not? And so if it's on Earth and it's not touching the floor, there's no floor down here that's shown. So it's not touching the floor, it's on Earth. There's definitely going to be the force of gravity on it. There's actually going to be the force of gravity on it, whether or not it's touching the floor or anything else, because just being near Earth means that you experience the gravity from Earth. So we've got the gravity from Earth, which is m1g here. Remember, the force of gravity is the weight. The force of gravity is the same thing as the weight. And the weight is the mass of the object times the acceleration due to gravity. m1, which is the mass of block 1, times g, 9.8 meters per second squared. That is one of the forces acting on m1. The other force acting on m1 is from the string. The string is holding it up. The string might not be doing a good job holding it up because you kind of presume that this is going to start spinning. If you just assume that m1 is heavier, has more mass, then m1 is probably going to be falling down, and m2 is probably going to be going up. And so you know that the string is still going to be pulling a little bit on mass 1. The string is going to be applying some sort of force to hold back m1, and in fact to lift up m2 over here. And that force, we call it the tension in the string. T is the abbreviation that we use. Whenever you have a string attached to something, you're going to have to deal with a force of tension, T, on that thing. And as we talked about before, the tension follows the path of the string. The string here is going straight up, and so tension goes straight up. The string over here is also going straight up, and so the tension goes straight up. You could rearrange this and, for example, put m2 like on a table, like move m2 over to a table that you put over here, and then the string would be pulling it this way, and the tension would also be to the left. If m2 is on a table over to the right-hand side, then the tension would be to the left because that's where the string would be pulling it. Another interesting thing to note here, look at the way that the free body diagrams have been drawn. The length of the T vector, the T force, the force of tension, is the same in both masses. Force of tension, the length of that is the same in both. The force of gravity is greater over here than the force of gravity over here. The length of this arrow is greater for m1 than it is for m2. That indicates that the force of gravity is literally greater than, magnitude is greater than m2 than it is on m1. M1 has a greater gravity than m2 does, because the arrow is larger on m1 than it is on m2. We can presume, based on the way that these free body diagrams have been drawn, that M1 is heavier than or has a greater mass than M2. It also looks like that should be because we've drawn M1 to be larger than M2, but that doesn't mean as much as drawing the arrow to be larger there. Now, let's look briefly at our free body diagrams. Looking at our free body diagrams, we can say that the net force on M1 is going to be the tension, which is up, which is positive, minus M1 times G, minus the weight, because that's down, that's negative. If tension up is smaller than gravity, the force of gravity down, then the net force is going to be down on that object, on M1. If the arrows pointing down are larger than the arrows pointing up, then there's more arrow pointing down, and so you have a net force down. That would indicate that if you have a net force down, then the acceleration will also be down, which makes sense. If we actually built this in real life and M1 has more mass, then M1 would fall down and M2 would be pulled up. And looking over here, we've got tension minus M2G, and tension is larger than M2G. And so you'd have a net force up in that case, and so M2 would accelerate up. Interesting thing here, the tensions have the same length, as I already mentioned. That is because the two forces of tension are the same. One of the interesting things about material science is that in general, if you don't have anything weird going on, and we will very rarely have anything weird going on, and I'll give you a warning before we do, the tension along a string is the same at any point along the string. If you have, and really, okay, what do we have? We have two ends of a string. I can talk about, the tension along a string as much as I want, but you really rarely attach something halfway along a string. That's not common. You usually attach things to one end of the string or the other. And so fundamentally, we just have the two ends of the string. And so this end of the string at M1 will have a force of tension T. This end of the string at M2 will have a force of tension T, and they're both exactly the same value, the same magnitude. The direction could be different. In this case, the direction is both up, but that's not necessarily always true. As I said, you could take M2 and put it on a table over here, and then the tension would be going to the left instead. Then you'd have a tension that's up and a tension to the left, and that's okay too. The magnitudes would be the same for both tensions. That is something important to remember for this class, that the tension in the string is constant at any point on the string, or in other words, the tension on the string on one end of the string is the same as the tension on the string on the other end of the string. We will do a couple examples much, much later where that is not 100% true. But for now, and for almost all cases, that is going to be a true statement. Tension is equal on both sides. Could you have the thing dangling from M2 and tension would be down? So if you completely removed the pulley, let's say, and just held M2 in the air, and it was attached to M1, then, and you're holding on to M2 above M1, then M2 would have a tension pointing down on it, and M1 would still have a tension pointing up because it'd be supported by the string, which is supported by M2, which is supported by your hand, if that makes any sense. This is all the math that we're going to need to do for this. It might look a little bit intimidating, but don't let that affect you. We start with exactly what we had on the slide. We've got M1 and M2 connected by a string over a pulley. I've redrawn the free body diagrams here. I did not actually show that the lengths of the vectors are different because I'm not that quick with drawing. So you can just pretend this is the more general way of doing things anyway. But what do we do with this? Well, Remember when we were doing two-dimensional kinematics? And in all of our two-dimensional kinematics problems, we would do a kinematics equation for one direction for x, and we'd do a kinematics equation for y. And between x and y, we would actually be able to see everything that we needed to see. We're going to do something similar here, where we have an F equals ma for this, and an F equals ma for this. Now, in kinematics, in two-dimensional kinematics, you would have one equation for each dimension. In this, you have one F equals ma for each dimension and direction. And this is kind of convenient because everything is just going in the y directions. You could have, say someone came in here and set up a fan right there, I don't know, some kind of fan right there blowing on M2. Then you'd have another vector pointed off that way on M2 as M2 gets blown that way, I guess. Well, that would change all of your values here. All of your free body diagrams would change because suddenly you'd have to pay attention to the x direction as well. As it stands, we've only got y directions, but we've got two objects. So we need to have two F equals ma equations, but each of them will be in the y direction, one for this and one for this. Let's look at this one first. I write down F net. This is understood to be F net y because it is going to be operating in the y direction, but because there's no x, I don't really need to write it down. F net, the net force, is equal to m1 times a. F is equal to ma, but you see I put a negative sign right there. This block is going to be accelerating down. So really, this negative sign is for that a right there. That right there is something to pay attention to. Sometimes you're going to have to say that the acceleration is negative or positive or zero sometimes. In this case, the acceleration will be negative because it's falling down. And so you can just add in a negative sign for the acceleration or with the acceleration, but of course it's going to get distributed out like that because of algebra. That right there, that little negative sign is responsible for a lot of people getting this kind of question wrong. If you have any questions about that negative sign, any kind of difficulty understanding that negative sign, then please tell me and we will talk about it. Until we get to that, we can replace F net with the things that make up F net, the net force on object one. Well, as I said, we've got the tension pulling up and the force of gravity pulling down. And so I can replace F net with all the positives, tension, minus all the negatives, gravity. And that gets me, let me cover up some of that. That gets me this. We have the tension minus the mass times the gravity. The tension minus the force of gravity is equal to the negative of m1a. Now I do see questions about that negative sign again. I think actually one way to explain this is to go on to object 2 and show how I do that and then go back to object 1. So bear with me a little bit and maybe it'll make more sense after seeing that. So T minus m1g, the tension minus the force of gravity, is equal to negative m1a, the mass times the acceleration. I can do some pretty quick algebra on that and see that the tension is equal to the mass 1 times gravity minus m1a there. So that was just some algebra. Then I do all of this again for object 2, which is here. F net on object 2 is equal to m2a, and this one is positive. Think about it this way. M2 is accelerating up because it's lighter. We're declaring that it's lighter, so it should accelerate up. M1 is heavier, and so it should accelerate down. We are just stating the obvious, that this acceleration is negative and this acceleration is positive there. Block 1 will have a negative acceleration because it's accelerating down. Block 2 will have a positive acceleration because it's accelerating up. We can do the same thing that we did on the previous one and say F net for block 2 is going to be all the positives minus all the negatives. So positive tension minus negative M2G is equal to M2A positive because it's accelerating up. Maybe that's the best way of explaining it. You account for the acceleration on this side and you say, well, acceleration is positive, negative, or 0. And if I can tell if it's positive, negative, or 0, I'm just going to include that in there. So this has to be negative and this has to be positive. Here's a thing to think about. What if you had positive accelerations on both sides? If both of these, if this was positive and this was positive, that would imply that both are accelerating up. When you let go, if say you're holding onto one and you let go, both would accelerate up, which is not really reasonable. If you have positive accelerations on each, then they would both accelerate up when you let go of them. To have one accelerate up and one accelerate down, you need to have different signs on them. That's probably the best way of explaining it. We then have this thing here that we got from block 1, this equation. Now, notice, we're just doing this all with variables. I'm going to solve for the acceleration. That's what the problem told me to do, solve for the acceleration. And so I've got this, I've got this, I want to solve for acceleration. Easiest way is to replace this tension with this function there. The tension is equal to that, so I can just replace tension with that. And so I do that here. The tension has been replaced with that. Right there, tension is that. Minus M2G is equal to M2A. Then I can do algebra. To solve this for A, I need to get everything with an A on one side and everything without an A on the other side. So I need to add M1A to both sides. And that gets me this. I did one more step of algebra here. I got M1A over here, and then I factored out the M1 plus M2, and I factored out the M1 minus M2 for M1G minus M2G right there. And then you just divide both sides by M1 plus M2, and you get that the acceleration is equal to M1 minus M2 over M1 plus M2 all times G. That looks like worse of an equation than it really is. So let's talk about what we can learn from this equation by itself. We assumed that M1 is greater than M2. And so M1 minus M2 is going to be a smaller positive number. It's not going to be as large as M1. M1 minus M2 is going to be less than M1. And then you divide by something that's greater than M1. M1 plus M2 is going to be greater than M1. So something less than M1 divided by something greater than M1, that's going to create a number that is less than 1, somewhat less than 1. So we have a number less than 1 times G. G is 9.8, so we have a number less than 1 times 9.8 meters per second squared. Our acceleration is going to be less than 9.8 meters per second squared. If you have a large mass and a small mass and is set up like this and you let one of them go, then this will accelerate down, but it'll accelerate down at less than the acceleration due to gravity. On the other hand, if you say that M2, actually, we made a mistake, and M2 is greater than M1. If M2 is greater than M1, then this number here becomes a negative number. If M2 is greater than M1, this is a negative number. That's ignoring our note that this one is heavier and this one is lighter. We're switching that heavier and lighter over there. This becomes a number that is negative now And so we have acceleration is equal to a negative something. The way that we defined this is that if it accelerates this way, that's a positive acceleration, and if it accelerates this way, it's a negative acceleration, which would be, as we see in chat, that it would be a decimal amount. It'd be a less than 1 amount of gravity. So it would be less than the acceleration due to gravity. Let's do another weird situation. What if I came in here and I replaced the lighter one with a single atom? Let's say that I replaced the lighter one with something with a mass of 0. Effectively, just that would be the same as coming in and just snipping the string right there. If you just came in and snipped the string right there, then this end of the string would not be supporting anything whatsoever. And so M2 would have a mass of 0 at that point. Like the mass on the end of the string would be 0 because you've cut off that end of the string. If M2 is 0, then we cover up M2 there, we cover up M2 there, and we say, oh, M1 over M1 is 1 times G, 9.8. The acceleration of that would be 9.8 meters per second squared, which would be just gravity, which is exactly what we'd expect if we snipped the string right there. If we snipped that string, this thing would just fall down unimpeded, unencumbered by any other mass trying to hold it up. So that makes perfect sense. Let's do another situation where M1 is equal to M2. What if these two masses were the exact same mass? Then we know that if they're the same mass and you let go of one, well, it's balanced, and so it should just kind of sit there, and it shouldn't accelerate if the two masses are equal. Does this equation agree with that? Well, if M1 is equal to M2, this is 0. M1 minus itself is 0 over, I don't care, that it's still 0. So the acceleration would be 0 if M1 is equal to M2, which is exactly what we would expect given our intuition about this object. If you actually built this object, we would expect all those things that we just said. That right there is one of the beauties of doing physics problems like this. One reason I really love physics is because you can get an ugly looking equation like this and then see by just like plugging in different kinds of possible values that this equation tells you exactly what you already think is going to happen just based on your intuition. That's really neat, I think, that we can do this much math, which, okay, it looks not great, but honestly, it's just a few algebra steps and like how to set up that stuff. That right there can tell us everything that we already really expect, but show us that mathematically accurately instead of just based on how we would explain it in a sentence. So I think physics is really neat because you can do exactly that with it.